Make sure to like and subscribe right now. Yes, do it.
Hello, this is Rick, and today we're going to be doing the number 25 from the AMC 10A of 2021 Fall Edition, or the number 23 from the AMC 12A of 2021 Fall Edition. This is my first year taking the AMC 12 exam, and for me, this has to be the most memorable question. I know it showed up on the AMC 10, but for me, this will always kind of feel like a more AMC 12 level problem due to the extensive knowledge of polynomials included and the fact that it was the number 25 on the AMC 10. So that kind of shows you how much harder the AMC 12 is than the AMC 10. But nonetheless, after doing some research on the problem, it is surprisingly not too bad. I wouldn't say it's an easy problem. I would definitely say it's mid to high AIME level, so 8+. But this problem isn't as bad as it seems, and it actually has a pretty good and pretty elegant sort of solution. So without further ado, let's just get into it. A quadratic polynomial with real coefficients and a leading coefficient 1 is called disrespectful if the equation pp of x equals 0 is satisfied by exactly 3 real numbers. Among all disrespectful polynomials, there exists such polynomial p of x for which the sum of roots is maximized. What is p of 1? So let's say we have some polynomial p of x equals to x minus r1 and x minus r2. We put a is equal to 1 because it says the leading coefficient is 1. So this kind of helps us get an understanding. Well, this is just the basic form of a quadratic polynomial. If we know that p of x is equal to 0, we know that in order for this to work, we know that for p of x to be equal to 0, then either the inner part p of x is equal to r1 or it's equal to r2, right? As subbing both of these values into our initially defined polynomial would give us 0. So this is a bit interesting. We know that this would yield exactly 3 real numbers for our initial x, such that the solution would be 0, based on the definition of the disrespectful polynomial. In reality, we're putting a quadratic function inside of another quadratic function, right? So that would give us a function with the highest degree, to the 4th power. So that since the highest degree is to the 4th power, right? Typically, we would expect 4 real numbers to be the solution. So the fact that there are only 3 real numbers as a solution, that kind of insinuates that one pair of solutions is a double root. So let's say that R2 is would be our double root. So here, what do? We kind of just summarized this first sentence in terms of mathematical expressions. We basically defined a p of x with a leading coefficient of 1. We showed how it could be equal to 0. And we kind of showed how this would be satisfied for only 3 real numbers. Now the next part of the question is a little bit trickier, but still not that bad. So what does it say? Among all the disrespectful quadratic polynomials, there's a unique such polynomial for which the sum of the roots is maximized. So when I think of maximizing a polynomial, I always think about the vertex form for that polynomial. So the vertex form for p of x we can write as p of x equals 2x minus h whole squared plus k. Now connecting this vertex form equation and this information we noted down from the first sentence, we can actually connect both of this information to obtain more knowledge about disrespectful polynomials. So since we know that R2 would be a double root, that would tell us that we can actually substitute R2 for k, right? And as this would give us our sole maximum value. So doing that, we get p of x equals 2x minus h whole squared plus r2. However, we can go one step further. Remember we wrote here that p of r2 is equal to 0. So we could actually substitute r2 for x. And we get p of r2 equals to r2 minus h whole squared plus r2. Expanding this out, we get that r2 squared minus 2r2h plus h squared plus r2 equals to 0. And then we can factor this into r2 squared minus 2h minus 1 times r2 plus h squared equals to 0. Well, now, as we know that so now we have a polynomial for R2, and we can actually use another property of a quadratic, the discriminant, to get some information regarding h. So remember what the discriminant tells you, right? It tells you what values the coefficients would have to be in order for your solutions to be real, complex, and so on like that, right? In the problem it says that the roots are real, right? So we know that this polynomial would have a discriminant that has to be greater than or equal to 0. So what does that mean? B squared minus 4ac has to be greater than or equal to 0. Right? What's our b in this case? Our b is 2h minus 1. So we got 2h minus 1 whole squared minus 4. Our a in this case is 1, right? Because there's no coefficient behind the r squared. And our c is going to just be h squared, right? So we get 2h minus 1 whole squared minus 4h squared is greater than or equal to 0. We know that the 4h squares are going to cancel out, so ultimately we get 4h minus 4h plus 1 is going to be greater than or equal to 0. So then we get that 1 is greater than or equal to 4h, which means that h is less than or equal to 1/4, right? Oops, it's coming out a little bad, but h is less than or equal to 1/4, right? However, it wants you to maximize the sum of the roots, which in this case is our which in this case would be our h, right? So maximizing this, we would actually just take h is equal to 1/4. Now since we got h, we can get the value for k, which we already said is the same as r2, by substituting h equals to 1/4 into this equation here. So doing that, we get r2 squared minus 2h minus 1, which should give us plus 1/2 h. Yeah. So 1/2 r2 actually. Oops. Plus 1/4 squared, so 1/16 is equal to 0. Doing some factorizations on this, we find that this is pretty much the same as r2 plus 1/4 whole squared is equal to 0. So that gives us that r2, which we already said to be equal to k, is equal to negative 1/4, right? So then we can actually use all this information and replace our initial vertex form polynomial for p of x, and we can just replace these coefficients h and k with their actual values that we solved for. So we can write that p of x is equal to x minus h squared, which we found to be 1/4, maximizing it, plus k, which we found to be negative 1/4. So then subbing in for p of 1, we get that p of 1 is equal to 1 minus 1/4 whole squared, 3/4 squared, 9/16 minus 1/4, 4/16, which will give us our answer of 5/16, which is answer choice A. So we solved the AMC 10 2021 fall edition number 25, or the AMC 12 number 23 2021 fall edition. Nonetheless, this is not exactly an easy problem, but it was a little bit tricky. But we went about this by first converting this first line into a mathematical expression, using the keyword of maximizing to come up with the vertex form equation, and then using our initial lines, and then we just kind of just algebra'd through it. We expanded, we used the discriminant, and we solved for h, substituted back for k, and then we got our polynomial, which is our final answer. So this just shows that even with the hardest problems, right, you just need to do the clear steps, right? Convert the algebra into equations. Pay attention to the keywords, and you can just follow through, like clear math, and just converting the words to equations will even help you solve like hard problems like a number 25 on AMC 10 or a number 23 on AMC 12. So I thank you for watching, and I hope you enjoyed the video.